All right, this is lab number 3, acids, bases, and buffers. Okay, so make sure you have lab 3 document in front of you as we go through this. All right, so when we talk about acids and bases, and we'll get to buffers near the end of the lab, but when we talk about acids and bases, we're actually talking about water molecules and how a water molecule may dissociate, may break apart, okay? So if we have a molecule of water up here, H2O is water, okay? It can dissociate, okay, break into pieces into hydrogen ions and hydroxide or hydroxyl ions, okay? So when we're looking at this, if it's even, okay, it's balanced, okay, then we're kind of at a neutral state for our pH, okay? So pH just kind of talks about how many hydrogens are present, okay, in that solution, the concentration of that. And it's actually, the first sentence of our lab says it's a log function, okay? And a log function means that it's multiples of 10, okay? So when we look at this diagram in your lab, you're going to see that it's not by tens, it's by ones, right? 0, 1, 2, 3, 4, 5, all the way to 14, okay? So it goes from 0 to 14, okay, or 1, okay? And so when you're looking at that, the log function says that from here, 1 to 2 is really 10 times difference, okay? 10 times more or 10 times less, depending on which way you're going, okay? And so that's what we're talking about when we're talking about pH. What is the concentration of hydrogen ions, okay? And then how many more, right? 10 times, 10, 10, 10, 10, 10 times, right? So 10, 100, 1,000, 10,000, etc., okay? More, okay? Or if you go the other direction, and I'm going to explain a little bit when we go through this, okay? You may have hydroxide ions, okay, or hydroxyl groups, hydroxide ions, okay? And if you have a high concentration of those, then you're going to be becoming more basic, okay? So we have 3 questions here, and it's going to help us kind of narrow down this diagram for us to kind of get an idea about pH, okay? If these are balanced, okay, if it's the same amount, then we're going to say that that is neutral, okay? So what pH is neutral? I actually need to pull this down just a little bit so I can reach that. Okay, which one is neutral? Well, our diagram tells us 7 is neutral. 7, okay? That's neutral. That means that the amount of hydroxide ion, the hydrogen and hydroxide ions are balanced, okay? They're at an even ratio, okay? Kind of at a balanced state homeostasis. Okay, we're going to see that again a little bit later. Okay, if the hydrogen concentration is higher, they're going to start getting to where we are being acidic. Okay, so below 7 starts getting acidic. So below 7, so 6, 5, 4, 3, 2, 1, okay, would be more acidic. What pH is acidic? And I'm going to put below 7. So 6.9 would actually be considered acidic, but I'm just going to kind of keep it generic and go 6 to 0, okay, going down, 0 to 6, okay, I can go that other direction as well. I'll go 0 to 6 pH, okay, and probably 6.9 would be a little bit more specific, okay. Anything below 7 is going to be acidic. That means it's going to have a high amount of hydrogen ions. Higher amount of hydrogen ions, okay? If you go and move the other direction, okay, anything above 7 is going to be basic. So above 7 is going to be basic, okay? That actually means that there's a few more hydroxyl ions and a lower amount of hydrogen ions, okay? So let's see, so we'll go 7.1, okay, still pretty close to neutral, okay, all the way up to 14, okay, pH is considered basic, okay, above 7 is basic, okay, and each time you move from one pH value to the next, you're going to be increasing that 10 times, okay, so if we say that this 7 is neutral, If I move to 8 and I say we went from 7 to 8 pH, okay, that is 10 times more basic because I'm moving to a higher number, okay? I'm above 7, okay? So 10 times more basic. And 10 times again, and 10 times again. So this would be 100 times more, and 1,000 times more, okay? So moving just one pH value is really a big deal, okay? Especially when you're talking at the microscopic level in the cells, and we'll get to that when we talk about the buffers, okay? You can do the same thing when you move to the acidic side, okay? If you go below 7, then it's 10 times more acidic, okay? All right, so that's the basics of this chart and how to read it, okay? You need to know neutral, and you need to know which direction is basic, okay, above 7, okay, 8, 9, 10, all the way to 14, and then which direction is also acidic. And you also need to know that moving from one pH to the next number, okay, is also 10 times more or 10 times less, depending on which direction you're moving for those numbers, okay? So make sure that you look at that. All right, the first procedure, this is not a really long lab, but the first procedure that we're gonna do, let's see if I can get everything on here real fast. Actually, let me make one adjustment. Erase this for us so it's nice and clean. This marker is darker for you guys. We're using this marker so it can be seen better in the video, but it does not come off the board really well. So. Alright, that should do it for us. Okay. So the first procedure that we're going to do is we're going to test the pH of several different compounds and products, okay? And I have a spot plate here, okay? And what I want to do first is tell you that we do have one change in what we're testing, okay? We don't have coffee, okay? I put cranberry juice in there. Okay, so you can make that change, okay, on your chart, on your lab, okay? So you'll see it's reddish color, it's not coffee, okay? So you go ahead and make that change, and then I'm going to move that up, and then we're going to test the pH of each of these with pH paper, okay? So, I'm gonna try to figure out how I'm gonna do this with and be able to write on there. I have to put it on her paper, I think. Sorry, technical difficulties. I'm gonna put it over it, I guess. Okay, all right, so what we're gonna do is we're gonna test the pH of these compounds, okay? And in well number 1, we have vinegar, and then milk, and then apple juice, grape juice, cranberry juice, okay, buttermilk, etc., all the way through, okay? All right. So now that I figured that out, sorry for the technical difficulties there, I'm going to pull that down so I can you see that over me? Yeah? All right. All right, so I'm going to take the lid off. And we're going to need to be able to tell which well is which. Let me get this all spaced in here. Takes me just a second. I don't use the dot camera quite as much as Miss Russ, so it's going to take me just a second. Yep. Okay. All right. So what we're going to do is we're going to test the pH, and all we do is we have some pH paper. Okay. And just to begin with, I'm going to have this up here. We have a pH kind of chart, okay, for us to read by, and then we're going to use our forceps, okay, and I'm just going to get a piece of pH indicator paper, okay, and it has a chemical on it, okay, it has a chemical on it that will change colors based on the amount of hydrogen that's present in that solution, okay. So So it's a pH indicator, okay? And indicators usually change colors, okay? You'll see that we do another lab later where we have color change, okay? So what I'm gonna do is I'm gonna put this, I'm just gonna take these 4 steps and I'm gonna dip this paper, this yellowish kind of goldish paper, into one of these wells, and then we're gonna see the color change. And I'm gonna use this table, okay, the chart, the standard, to estimate what the pH is, okay? So if I dip it in the vinegar, it goes from that yellowish gold to kind of a orangey red, okay? And so I would compare it to all of these, and obviously it's kind of closer to over here, okay? Kind of pinkish, reddish, orange. It's not gold, it's not green, it's not purple, okay? And so I would take this and I would say, okay, that's probably a pH of 1 or 2, okay? And I'm just gonna set that off to the side. And I wanna read it right away, because after a while, I'm just gonna add pH right there, okay? 1 or 2, and it kind of just depends on your eyes and how you're seeing that, okay? After a while, it will change colors back, or it'll change a little bit differently as the indicator wears off. So you want to read that right away, okay? And so I'm just going to take the next one, clean my 4 steps, and put it into the next one. And this is milk, okay? And it started out this yellowy gold color, and it looks like it kind of stayed that yellowy gold color. We're going to zoom in, or can we see it? Zoom in? Okay. I'm going to move this out of the way. Okay, so if I look at this, it's going to be pretty close to that same color. Still not seeing the color very well, huh? Better if I lay it down. Right, if I look at this, it's really that same color as that 7. Okay, so I'm going to say that the milk is a pH of 7 that is neutral. Okay, it's not quite that orange, and it's not this greenish color. It really looks a lot closer. It almost looks like the same paper that it started with. Okay, if I use the next one, and this is going to be apple juice. I'm trying to lean over so you guys can see. Apple juice, it goes from that yellow to a brighter orange. Okay, and I'm going to kind of go across. I'm looking, it's not quite 4, a little bit lighter than 5, so 6, 5, 6. Okay, and I just kind of have to look and see where it kind of matches. So I'm going to put 5 or 6. I don't have that on the paper. Okay, for the apple juice, 5 or 6. We said milk was 7, and that was 1 to 2. Okay, 1 or 2. All right, moving to the next one. We're going to go from this yellowish orange color to well number 4, and this is the grapefruit juice. It's also more orange than 7. 7 is neutral. Okay, so I'm going to move over here, maybe 6. I think it's actually pretty closer to 4. It's really pretty acidic right there. Okay, so to me it matches that number 4. So grapefruit is about 4. It's acidic. Number 7 is neutral. The next one on your paper says coffee, but remember we changed it to cranberry juice. Okay, this reddish color one. And look how fast that changed colors when it was in there. Okay, this was the original paper. This is what it is now. Okay, there's a huge dramatic difference. Okay, that's way over here. Okay, and it looks really very acidic, almost 2. Okay, so I'm going to put 2 on there. Remember, this is cranberry juice. right, the next one is buttermilk. Trying my steps. Right, and buttermilk versus milk, right? Milk was 7, okay? We saw it stay about the same, right? And so now I have this buttermilk, and it's pretty close to the same too, as well. It's not quite as golden yellow. It's a little bit more orange in it than the first one. So I'm gonna say it's like 6, okay? It's a little more orange, it's not quite as yellow, okay? So that's a little more acidic than milk. Buttermilk is a little more acidic than milk. The next one is Sprite. Next one is Sprite. Right, dip it in. Compare it to the original paper, okay? And it's a bright yellow, okay? It looks very close to our neutral, okay? But if I hold it next to the 6, it's a little bit, it's not quite 6, but it's also not quite 7, okay? So I'm gonna say it's just below 7, okay? Because of the carbonation in Sprite, or in sodas, in Cokes, okay? Carbonated drinks, you're going to have a little bit of acidity. So I'm gonna put 6. Okay. The next well is baking soda. Okay, and baking soda, you can use it for cleaning. You can use it. Some recipes call for it in the recipe for baking. It's just a white powder in the orange-looking box. Okay, and I'm going to dip it in there as it's sitting at the bottom. So I'm going to stir that up to make sure that I get it to touch the baking soda. Okay, and all of a sudden, this first one now is the first time that we're seeing something greenish. Okay, and so I'm going to kind of dry this a little bit so I can hold it over the scale, and it's a light green. Okay, so this is close to 8. It looks about the same as 8. 9 is a brighter green than that, than what I have in my hand. And so I'm gonna put 8 on the baking soda, okay? Usually we get a pretty high pH on that. It's usually 10 or 11, but for whatever reason today we only got 8, but it is on the basic side, okay? That's the first one that we see that's basic so far. Okay, all the other ones we had have been neutral or acidic. All right, this next one is tea, okay? Just iced tea. And it is pretty close to, I had a little bit of baking soda on my, do that one again. A little bit of baking soda still on my forceps. Made it turn green. So tea, iced tea, sweet tea. Here's the original paper that I just made wet. Okay, and I'm going to hold it up to that indicator, to the key, and it's going to be close to 7. Okay, close to 7. So tea, the tea that I have here today, is close to neutral. All right. The next one is hydrochloric acid, HCl, hydrochloric acid. Okay. Dramatic change pink. Okay, dramatic change pink. And I'm going to put 1 for that. Okay, very acidic. I'll put 1. Okay. Hydrochloric acid is already labeled for us as acid. Okay. The next one is distilled water. Distilled water. I'll get that acid off there. Distilled water. This is water that's been purified and processed. That should be clean, only water molecules. Okay. This is the distilled water that's in a tank here at San Jac, okay, on campus. Distilled water should be neutral, especially if there's not any other ions in it, okay, or molecules or compounds in it, okay. So it should be neutral, okay, and it is. It looks like a golden yellow, okay, golden yellow. So distilled water is 7, okay. That means the distilling process is working. It's keeping it pure water to where that pure water would dissociate like we talked about at the beginning, okay, and be balanced, okay? And the last one is tap water just out of the faucet here at San Jack in the lab. Got one more, last one. And this one actually turned a little more like limey color, right? Like a lemony green or a unripe yellowy lime, okay? It actually is a higher pH of 8, okay? We think that water should be close to 7, and it's not far off, okay? But when I look at this one, it looks a little more greenish yellow, okay? So I'm gonna put 8 on that, okay? And if we were in class, we'd probably take a poll of how many tables had 7, how many had 8, and we would have a little bit of variation there based on how you're reading that color, okay? And so you're gonna see a little bit of change there, okay? All right, so what does that mean, okay? That means that different substances have different pHs, okay? Based on what is in there, okay? Let's move it over just a little bit so we can see the name of it with that. Okay, and so we can see that there are a few things that are neutral, okay? I have never tested this tea before, so kind of pleasantly surprised that it's kind of neutral, the tea. Maybe it's a lot more water than tea in there, because sometimes tea is a little bit acidic. If we test like a specialty tea, then we've gotten acidic before, okay? So vinegar, okay? Vinegar is something that we use for cleaning, for pickling, for canning, okay? And it's going to change the molecular structure of some compounds, okay? And so it's very acidic, a low number, below 7 is acidic, okay? Milk is pretty neutral, okay? And buttermilk is a little more acidic than that, okay? That extra lipid, that extra fat that's in there is making it a little bit more acidic. It's fatty acid, okay? So a lot of the things that we take into our body are close to that neutral or just barely acidic, okay? Grapefruit juice and cranberry juice, okay, both very acidic, okay? And then you're going to be looking at this baking soda, and again, we usually get a higher read on that. I didn't test that one before the video, but it's usually a little bit higher, but it is right now the one that is looking like it's the most basic for us, okay? So the 3 questions right below this table, okay, are which substance is most acidic, and I'm hesitant to move it up because then we get off the screen there, okay? So which one is most acidic, okay? And the most acidic was either the hydrochloric acid or the vinegar. If I read it as 1, then they would both be a pH of 1. Lower, below 7 is acidic, okay? The next question says, which substance is the most basic, okay? Basic means it has the highest number, okay? So baking soda has 8, okay? It's above 7, that means it's basic. And the tap water also had 8, okay? Why, if water is supposed to be neutral, why is the tap water 8? Well, it might have some other particles in it, okay? Maybe maybe there's some debris, or maybe there's some growth in the pipes or something like that. Maybe there was something in the flask that I took the water out of, okay? Maybe the container that I took it, because we just put it in a beaker, and then I pulled some of it out of there. So maybe there was something in the beaker, okay? But it should be close to 7, okay? So anyway, back to the question. What substance was the most basic? Baking soda and tap water, okay? But baking soda should be more basic, okay? Which substances were neutral, okay? Neutral is 7, okay? So we had milk, and we had tea, and we had distilled water, okay? All as neutral, okay? So a lot of times it just depends on what we want to put in our body. So some people have a hard time drinking grapefruit juice because it's really acidic, okay? Some people say cranberry juice will help filter and clean out your kidneys and things like that. I don't have any data for those things, but those are rumors that are out there, okay? So it just depends on what we're looking at, okay? As this carbonated drink would sit for a while, and that carbonation, if it would go flat, okay, that pH would change, okay? All right, so going on to the next procedure. Down. Next procedure. And we are going to look at a buffering system. Let me zoom out, I think. Ow. Gotta be smarter than the technology. Okay, so we're going to be looking at buffers, okay? So pH, why are we talking about pH? Why do we have a lab about pH? Well, pH is actually really important for molecules to work, okay, for reactions to happen, for enzymes to be active, okay? They're really important in an organism, okay? But we also, like we just talked about in that last one, we take in things that have different pHs. So if we take in something, or if a microscopic organism takes in something, what does that do to its environment, to its normal state, okay? Does it change that pH, okay? And that one number change, either more basic or more acidic, remember, is 10 times more, okay? So if I just go from 2 to 3, or from 7 to 6, doesn't sound like a big deal, okay? But it's a huge deal, okay? That's 0.01, okay, of a change in the concentration of hydrogen, okay? 0.01, okay? 0.01 change in the amount of hydrogens present, okay, in that environment. And that is enough to change the pH, okay? That is a pretty small number. But we're also talking about microscopic levels, okay, and at the element or molecule level, okay? So that is actually a big deal. To go from a pH of 7 to a pH of 6 is 0.01 difference, okay? 10 times more acidic, okay? And that can be detrimental to a cell, okay? To an organism, okay? So living things have what are called buffers, okay? And those buffers are going to help resist this change. They're going to have chemicals there that can help bind up all those extra hydrogen that become present, okay? You may have heard the term antioxidant, okay? Those are kind of molecules that can help these buffering systems and or help bind up these extra hydrogens and pull them out of the environment. Because when you have those situations where you're more acidic, okay, or more basic, but more acidic usually, you have more chance of having some DNA mutations, some cellular damage, your enzymes might, not yours, but in general, and organisms might not work, okay, as efficiently or at all, okay? It's just like cooking an egg. You're gonna see a lab later where we test enzymes with pH, and where we also talk about changing the temperature. You take an egg, okay, and you cook it, okay, you're changing that temperature, you're gonna change the bonds. You're gonna see that again later. But we also did one where you change the pH, okay? If you know anyone, or maybe you can, make pickles, pickled eggs, pickles, cucumbers to pickles, right? Anything like that, you're going to add vinegar and you're going to change that pH, right? Once you make it into a pickle, you can't change it back into a cucumber, okay? You have changed it forever, right? And so that little bit of change, okay, can affect those cells and those organisms really dramatically, okay? So we're going to test for buffers, and we're going to see that a buffer is going to help resist that change. It's going to help bind up those hydrogens, okay, and try to help maintain a steady pH, okay? And that would help for homeostasis in that living thing, okay? So I set up our well, our spot plate for the next one. Move it up. Put paper down so that I get this one as wet. This one might fit on here a little bit better. Do that for now. And put our chart. Okay, and I know these colors are a little bit hard to tell, to see. I don't want to put that chart too high up there because I have to write in it. Put that there for now. Okay, so what we're going to do is I have these 3 wells set up, okay, and there's liquid in them, 1, 2, and 3. directions. So the first one has distilled water, okay? The second one has a compound, okay, that has some chemicals in it called a buffer, okay? And the third one has some cytoplasm, right, like you would find inside of a cell, okay? The fluidy, liquidy part has enzymes and some other compounds and molecules in it, okay? And so we're going to test the pH, okay? I just put the 20 drops, I did step number 1, 20 drops, 20 drops, and 20 drops of those 3 compounds, solutions into those wells. And we're gonna test the pH, okay? We're gonna test the pH of each of them. And we're gonna record that into our chart, okay? We did distilled water in that last spot plate, okay? Let's see if it's still the same. Okay, it started out a golden yellow and stayed a golden yellow. Okay, so I'm going to put 7. pH before, okay, is 7. Okay, we're going to test it and we're going to add some hydrochloric acid, sorry, to this, and we're going to see if the buffer works and get some results. Okay, the next one is the buffer. Okay. The next one is the buffer. It started a golden yellow and is still a golden yellow. So it is also 7. And then the cytoplasm is last. And this is nice yellowy color starting. And we finish with a yellowy color, okay? With that golden yellow. So they're all 7 to start. Is that acidic, neutral, or basic? 7. 7 is neutral, okay? So we're starting out all 3 wells, all 3 spots are neutral, okay? I'm gonna add 0.1 millimolar hydrochloric acid, okay? I think it says 5 drops. 5 drops into each one. 1, 2, 3, 4, 5. Okay. And bring a stir rod. I'll stir these up just a little bit. Should be fine without stirring, but we just want to keep it pretty consistent. All right. And so now we added some hydrochloric acid. We added more hydrogens to that environment, okay? All right, so let's test our pH, all right? The distilled water was 7. I added hydrochloric acid to it, made it an acidic environment, maybe, right? And let's see, we're starting out this golden yellow. And we turned acidic, right? That bright pink that we saw at the beginning, right, when we tested hydrochloric acid, okay? That bright pink. So I'm gonna put 1, just like we did earlier, okay? If I take and test the next 2, see what times I am. Make sure I get in there. Right, started out golden yellow, and now I'm still golden yellow, right? That pH stayed the same. It stayed 7. That's kind of what we were expecting, right? Based on the definition of a buffer, right? A buffer is a substance or a compound, okay? A solution, right? Something that's going to resist a pH change. We added hydrochloric acid, and we know that hydrochloric acid is good, it's not broken down, because this distilled water changed from a pH of 7, neutral, to very acidic, okay? And so we added the same drops, okay? But it stayed the same, the pH did not change, okay? So that buffer is working, okay? We have 1 more to do. So the cytoplasm, like I said, is that liquidy, okay, semi-liquidy portion of the cell. It's what's inside of the cell, suspending all of the organelles, okay? And we're gonna test it to see. Started out yellow, and it stayed yellow. right? Stayed yellow. It's not green, it's not orange, it stayed that yellow, right? So the cell also was able to resist that pH change, that cytoplasm. Okay? So the cytoplasm inside of a cell has a buffering system. Okay? There's actually several different systems, right, that it would have in there. So it has some compounds that'll say, hey, there's too much hydrogen, activate this cycle, bind those up, because we can't have a pH change. Because this 10 times more pH change could be terminal for that cell, okay, and or for several of the molecules inside of it, okay? All right, so let's answer our questions, and then, which I may have done a little bit already, okay? Right, so the conclusions are also kind of in these questions here, okay, but we'll fill in the conclusions because we want to make sure we have a completed table, okay? So the first conclusion of well number 1, the spot number 1 with the water and then the hydrochloric acid, it went from a pH of neutral to a pH of 1, okay? Is there a buffer system there? No. No buffering. Okay? No buffer system. Okay? Why? Because a buffer will resist the pH change, and the pH changed when I added that hydrochloric acid. Okay? The second one is, the name of it is a buffer. Okay? It started at 7, we added hydrochloric acid, and it stayed at 7. It resisted a pH change. Okay? It is positive, it has a buffer system. Right? It's in the name. Okay? Buffer system. Okay? We're going to define what that means in just a second. Okay? The third one is the cytoplasm. It started 7. We added hydrochloric acid. It stayed at 7. The same result here. It also is positive for having a buffer system. Okay? Why did the pH change so dramatically in well number 1 but not in well number 2 and 3? Well, because it's no buffer system. It has no buffering ability. Okay? It's just pure water. It's just hydrogen and oxygen. Okay? That's it. There's no other chemicals in there to help bind those up. Okay? So when we added more hydrogens from here, from this hydrochloric acid, all it did was increase the hydrogen level. Okay? There was no way to bind those up. Okay? What is a buffer? A buffer is a substance, a chemical, okay, something, okay, some kind of substance that can resist a change in pH. It does that by binding up, okay, binding with those extra free hydrogens. Okay? Are cells buffered? Cytoplasm is inside of the cell. Yes, they are. Okay? Why would they be buffered? Why would they have that, and how do you know? Well, we know because of their test results, right? It started at 7, it stayed at 7, okay? But they need that to maintain homeostasis, okay? Why do we know that? Well, our test results show resistance to change. There's lots of ways to word that. And why do they want to have that? Well, they want to help maintain homeostasis. Okay? All living organisms want to be at a steady, balanced state, and that balanced state is homeostasis. If they like to be at 7, they want to be at 7. Okay? And so these buffering systems will help them maintain that. Okay? Basically, that's the end of lab 3. If you have any questions, make sure you